Okay, so let's continue. 3.8, okay? And right now, let's move on to talk about how to figure out the derivative of the natural logarithm, which is ln of x, okay? And a fact we already know that is the natural exponential function and the natural logarithmic function, those are inverse functions of each other, right? So we're going to borrow this fact to derive the derivative of its ln of x, okay? So I'm going to show you two ways. And the first way is to treat the ln of x is the inverse function of the natural exponential function and use the derivative rule for inverse function to figure that out, okay? So the derivative rule for the inverse, I think maybe this part, the line is better. So the derivative rule for inverse function is defined as this. So the derivative of inverse function equals the reciprocal of the derivative evaluated at the inverse function, which is defined like this, okay? So ln of x, which is the derivative of the exponent, which is the inverse of the exponential, it equals, again, reciprocal of, you see guys, the derivative of the original function, which is e to the power of x itself, okay? And then evaluated at its inverse function, which is ln of x. So we're gonna have it's 1 over e evaluated its ln x to the power ln of x. And also we know that the properties about the logarithmic is e to the power of ln of x actually equals x, right? Or ln of e to the power of x is also equals x. So we can get that the derivative of ln of x equals 1 over x, okay? So this is one way to think about this. The other way to talk about this is to use the properties, okay, about the a logarithmic can be rewrite into an exponential. So, suppose y equals ln of x. We want to figure out what is the derivative of ln of x. That is dy dx, right? So I can rewrite, take the exponential function on both sides. So I have e to the power y equals of x. So this is very natural transition. And on top of that, we're gonna use the implicit differentiation. We talked about that, right? In, I believe it's 3.7. And then as you see that, take the derivative with respect to x on both sides. Right hand side equals 1. Left side equals e to the power y times dy dx. Again, you're going to use the chain rule and treat y as a function of x. So our goal is to figure out what is dy dx. So dy dx equals 1 over e to the power of y, right? Again, y equals 1 over x, y equals ln of x. So substitute that back. You have 1 over e to the power of ln of x, still give you is 1 over x, okay? So those are the two approaches to derive what is the derivative of the natural logarithm function, okay? So let's move on to do one examples. And also, guys, here's the thing. If you take the derivative of natural logarithm absolute value of x, okay, as long as x is not 0, as you can see that this absolute value sign, it can take the positive or negative numbers as long as non-zero. And okay, so the derivative of this line of absolute value of x is gonna equals 1 over x, okay? So in fact, you can discuss when x is positive, right, when x is negative, and it turns out that the answer is all 1 over x, okay? So this is one result we can tell. The other thing is we're gonna extend this, okay? Suppose you have a line of u, again, u is a function of x. So So this becomes a composite function. So kind of use the idea of the chain rule. So if you're taking the derivative of 1 over u, if you're taking the derivative of ln of u, and that are going to give you it's 1 over u times du dx, okay? So now let me show you one example here. Suppose I have fx equals ln of x squared plus 3x plus 7, okay? And as you can expect, this inside part is a polynomial, right? It opens up. In fact, inside of this polynomial is always greater than 0 all the time for all the x, okay? So this is kind of like in this format. So to take the derivative of this, what we do here is make the reciprocal of the inside. So it's 1 over x squared plus 3x plus 7, okay? And then time the derivative of the inside, x squared plus 3x plus 7 derivative, 1 over u times du dx. Then this is going to give us is, this part is at 2x plus 3, so it's 2x plus 3 over x squared plus 3x plus 7. Okay, so this is what we get. A very simple example here. Okay, so now let's talk about another type of question, which is called this logarithmic differentiation. Okay, so let's look at one example like this. Okay, so I'm gonna erase here. So, okay. Let's look at one example, something like this. Okay, so some y equals x plus 1 cubed times x squared plus 3x plus 7, right, over, I don't know, so maybe x minus 1 squared, something like this, okay. And, you know, the question is, okay, let's take the derivative of this, okay. And you see, guys, this problem, it is okay to treat this problem as a quotient format, right? And so you can definitely apply quotient rule, but also the product rule to handle this problem, right? So this is called log differentiation. Okay, logarithmic differentiation. But let's try to think about it another way. Okay. So assume, okay, let's also assume maybe let me do, let's see, let's set x is greater than 1. Okay, a set x is greater than 1. Just easy for us to handle that. Okay. And why I try to set x is greater than 1 is I want to make sure that inside of the parentheses is all positive. Okay. So of course we can take the using the quotient rule and the product rule, but as you expect, you know, it can be very long, tedious, right, and very crazy, ugly result. They're gonna happen. But right now, let's try to think about another way to do that. You see, if we take a natural logarithm on both sides, okay, that is ln of y equals ln of x plus 1 cubed, right? X squared plus 3x plus 7 over x minus 1 squared. Okay, I should put up it correctly. Now, some of you might still remember there are several properties about the logarithm. when you have ln of A plus ln of B, it's gonna give you ln of AB, right? Ln of A minus ln of B equals ln of A minus B. Ln of A to the power of M equals M times ln of A, right? So those are the three very basic ones. You can tell that on the right hand side, we actually can decompose it into three pieces. Let me show you. First I can do is right, guys. So actually using the backwards of the second property, ln of A or B equals ln A minus ln B. So this is what we can get here. We can also use the backward property of part 1 to split this into two parts. That can give us is ln of x squared plus 1 cubed plus ln of x squared plus 3x plus 7 minus ln of x minus 1 squared. Okay, this is ln of y. Okay. All right. So up to here, you know, on the right hand side, we pretty much simplify into three logarithmic functions, right? And but can we do a little bit more? Well, the answer is yes. Okay. How do we do that? Well, we're gonna use the third property from the natural, from the logarithmic, not only for the natural logarithmic, okay, but for any types of logarithmic. And we can get this. So this is gonna equal 3 times ln of x plus 1 plus ln of x squared plus 3x plus 7 minus 2 times ln of x minus 1, okay? This gives us this ln of y, okay. Okay, so you see guys, right now, the right hand side, if I'm asking what is the derivative of ln of x plus 1, easy stuff, right? What is the derivative of this? Well, we can handle that. 1 over u times u dx. What is the derivative of this? Again, 1 over u times u dx. Okay, and you see up to here, we actually transfer the problem into a logarithmic format, okay? But still, we want to figure out the derivative of y with respect to x. That is dy dx. What I can do here is, I can take one implicit differentiation on both sides with respect to x. So, on the left hand side, it's going to give us is 1 over y times dy dx, okay? It equals 3 over x plus 1, right, times the derivative of x plus 1, which is 1, and then plus x squared plus 3x plus 7 on the bottom times the derivative of the top, which is 2x plus 3, and then minus 2 over x minus 1, again times the derivative of inside, which is 1. So you can see that, guys, left hand side is dy dx times 1 over y. Right hand side is this 3. Our goal, our final goal, is to figure out what is dy dx. Yes? Right? So do you see that it appears here? So I have 1 over y times dy dx. What I can do here is, do you see if I multiply a y on the left hand side, this y and y cross out, so only left dy dx here. This y, where's our y? Well, y gonna be here, right? So what you can do is, you can just copy this part and paste it to here. That is gonna give you dy dx, okay? And again, you do not have to combine all of this and then simplify. It might take a long time, but you got the basic idea is instead of using the quotient rule and the product rule to make the calculation long and complicated, you can take the natural logarithm on both sides and convert it into a logarithmic expression and use the properties about the logarithmic, and then we can simplify and then observe the result. Okay, so this I think this is a very good way and an effective way to handle the problem like in this type. Especially you have a rational function, either the numerator or the denominator have more than one part like this, this part times this. And under this type of questions, and the logarithmic differentiation can be very productive. Okay, so this is the end of the 3.8, and I'll see you in the next section. Bye.